Hello and welcome back to this course, covering the exam topics for the JNCIS-SP certification. In this section of the course, we're reviewing Layer 2 switching and VLANs, where we will cover Layer 2 switching mechanisms and Ethernet switching configurations in Junos. The Juniper EX switching platform is Juniper's current line of devices focused on enterprise switching. Although other Juniper devices also support Ethernet switching, such as the SRX and MX platforms, the EX platform is highly targeted and most feature-rich when it comes to implementing switching environments. In this lesson, we'll be taking a look at the differences between a shared LAN and a switched LAN, as well as the mechanisms at play in Ethernet switching. This video is titled Switching and Bridging Components. However, switching and bridging are terms which may be used interchangeably in our context. You may find in Juniper documentation references to both bridging and switching. These terms are interchangeable and refer to the Layer 2 operations involved with forwarding frames. Before we go over the bridging mechanisms, let's first review the differences between a shared LAN and a switched LAN. See, before switches were relatively cheap and easy to acquire, many network environments relied on hubs. A hub essentially takes multiple physical connections and merges them into a single wire. From the perspective of the devices connected to the hub, they see all other devices as though they were physically connected to the same piece of wire. Regardless of how many ports a hub may have, it will still only provide a single collision domain, and having a single collision domain for several connected devices will force the link to operate in half-duplex mode, meaning only a single device on the link may transmit at a given time. If you need to review collision domains or duplex, I recommend taking a look at the network terminology video in the Networking Fundamentals section of my JNCIA Junos course, also available on this platform. In addition to the obvious performance impact of operating in half-duplex mode, a single collision domain will allow all connected devices to effectively see all data that is transmitted or received within the collision domain. Remember, a hub essentially connects all devices to a single continuous wire. As you can imagine, this could certainly pose some security concerns with unintended recipients gaining access to potentially sensitive information. Hubs do not use or need any intelligence when forwarding data. As all data is seen by all connected devices, the traffic will be sure to reach its destination, along with all other connected devices. So, a shared LAN uses hubs. Now, let's take a look at a switched LAN. As technology has advanced, network switches were developed, which solved many Ethernet scaling problems, including those we identified with a shared LAN. A switched LAN forwards data to its destination intelligently by using a bridging table. This table contains a list of MAC addresses and what ports they can be reached on. This helps ensure the data is only received by its intended recipient. Each port of a switch is a separate collision domain. This allows for connected devices to operate in full duplex communication, where devices can transmit and receive simultaneously, enhancing the speed of our data transfer. Where a 48-port switch contains 48 collision domains, a 48-port hub only contains a single collision domain. In the next slide, we'll review the mechanisms that allow switched LANs to exist. Bridging allows for a mixed bag of interfaces to be logically grouped into a single broadcast domain. Where shared LANs could only operate at a single port speed due to the shared physical media, bridging allows for any type of physical interface media to be logically grouped into a single broadcast domain. As we mentioned before, bridging or switching forwards data based on the destination MAC address and a lookup in a bridging table. The bridge table is built using the mechanisms shown here. First, we have learning. This is the process by which the bridge learns which MAC addresses are reachable through which ports. The switch inspects ingress frames and notes the source MAC address, saving the information of which port that source MAC address was seen on to be able to forward any return traffic. Next, we have forwarding. This is the mechanism used to look up the destination MAC address seen on a frame and determine which port to forward the frame out of. If no match is found in the bridging table, typically a switch will flood the frame out all interfaces to ensure its delivery. This leads us into our next mechanism, flooding. Flooding is the mechanism by which a bridge forwards a frame out all interfaces within the same broadcast domain. This occurs naturally for broadcast frames, though can also occur with unicast frames where the destination is unknown, or sometimes multicast frames when the switch is not configured to handle multicast traffic otherwise. The filtering mechanism is used to control which data is forwarded. Traffic received that is tagged with the wrong VLAN or dropped by a stateless firewall filter uses the filtering mechanism. And finally, we have the aging mechanism, which ensures the information in the bridging table stays fresh and relevant. When a source MAC address is not seen on any ingress frames for a period of time, the bridging table entry is removed as the switch assumes it no longer knows for certain where that destination MAC address is located. We'll be reviewing each of these mechanisms in more detail in the following lessons. I hope that this lesson has been informative for you, and I would like to thank you for viewing.